So, good evening. Welcome to Krishna's classroom. We begin with another topic on metric spaces, which is an important concept. So, let X be a metric space. Now, just recall what we mean by the space is complete. Before that, recall that every convergent sequence in a metric space is a Cauchy sequence. So, this is what we have. Every convergent is a Cauchy sequence. By which we mean that if Xn is a convergent sequence and Xn converges to X, then we have given epsilon positive, there exists n belonging to such that for all m n greater than n equal to n, the distance of Xm that means the tail of the sequence will start getting closer and closer. So, for every convergent sequence, this can be easily shown. But there may exist Cauchy sequences in X which may not converge Now, this kind of sequences that we have are called Cauchy sequences. So, every convergent sequence is a Cauchy sequence, whereas every convergent sequence may not be, every Cauchy sequence may not be a convergent sequence. Now, we have the example. We know that R is complete, whereas Q the set of all rationals, which is a subset of R, in fact a subspace of R adopting the same distance function, is not complete. That is, there exists Cauchy sequences Cauchy sequences of rationals which may not converge to a rational number. So, Q is not complete. And this is one of the properties that we have. And essentially, the completion of Q is R. This is what we have. Now, these are the basic properties are, of course, Q is dense in R. Every Cauchy in fact, R has been constructed as the completion of Q. We shall not go into the details here, but we are already aware of it. Okay. So, to cite an example, you look at this one. N equal to 0 to consider the sequence. Which is a sequence of rational numbers. And it converges to does not converge and this sequence, is the sequence that converges to the exponential number. But the exponential number and E is not rational. So, the question that we ask at this stage is, see, we have Q as a completion. Every element of Q can be considered as an element of R, and every sequence, every rational sequence that you construct with elements in Q which are Cauchy sequences, converge in R and not in Q. That is the problem. So R is called the completion of Q. It's called the completion effect. Now, there are a lot of examples that you can cite having this property. So, in general, we ask the following question. So, the question is this. Given a metric space a completion of X, is it unique? So, see, in some sense, we see R is obtained or R is constructed as the completion of Q. And in some sense, it is unique. Okay. So, we shall ask this question in the context of a general metric space, which may be or may not be complete. If it is already complete, there is nothing to work on. But if X is not complete, then we have to try or investigate whether there exists a completion of X. So, we have to be clear about what exactly we mean by completion. So, let us recall the definition. Completion of a metric space. Let a complete metric space y Vy is said to be completion of X if there exists a map F from X to Y such that one F is an isometry of Y to Fx dense in what do we mean by F is an isometry? F is an isometry. F from X, Y is an isometry. If for every x1, that means the map, there exists a map F from X to Y such that the distance between 2 points remain invariant under this map. Namely, if fx1 and fx2 are the images of x1 and x2 in Y, then the distance between fx1 and fx2 is equal to the distance between x1 and x2. Because dx and dy represent the corresponding metrics in the respective spaces. Okay. So we want two conditions to be satisfied. So the given x, there is a y such that there is an isometry of x into y. Secondly, the image of x under F is dense in y. So if these two properties are satisfied, then we say that y is a completion of x. Now, if you return to our familiar example of Q and R, now you have Q B, the usual distance, R B. Now you define the map F from now you see that it's a isometric. Further, what you have is that Q is dense in R. Okay. So we can approximate every element of R by a sequence in Q. In short, or in other words, we obtain that all Cauchy sequences in R converge in R, whereas all Cauchy sequences in Q may not converge in Q, but it will converge in. So R is the completion of Q. Okay, so R satisfies all the conditions that we have set for to be a completion of Q. Okay. Now let us try to work out this problem. Now meanwhile, we will just give some examples of isometry just to be familiar with what property is all about. Make some noise about isometry. A map F from X into Y is called an isometry. In fact, you see that the identity map provides you with an isometry of Q into R. That's an example. Now we'll look at some examples. Make some remarks about this property. Let be then is complete if and only if Y in fact here we take F to be onto. Now as that is one of the properties, the second remark I want to make is this. An isometry is a one-to-one continuous. We look at some examples here to understand this. the usual metric. Fine. Where z is equal to x plus I by is an isometric. Second example, on any normally linear space, x, the translation bar for every x belonging to x, z belongs to is an isometric. That's quite easy to see. Now the third example is that the orthogonal map defined by for every x belonging to Rn. This is because so you have Ax, Ay equal to Y transpose A transpose A x so that is these are some of the examples of isometry. And we shall not be too much bothered about it. Yeah. Now we have already defined what is called a completion of a metric space. Now we have the following examples. The first example is what we have discussed. Q R is a completion. Two if x dx and if x dx or let me give an example. Second example is this. The set of all polynomials Px, P is a polynomial with norm defined by norm of P that is the sup norm then C01 all continuous functions of the interval 01 with sup norm is the completion of and V as such is not complete, whereas C01 is complete, and every continuous function on the interval 01 can be approximated as closely as you want through polynomials on interval 0. This is the Weierstrass approximation here. Shows that all Cauchy sequences of polynomials do converge in C01. If you take the sup norm, of course, if you change the norm, it's a different story altogether. Okay, So let us just leave it there. Now, how do we hope to obtain the completion of this space? Let us return to Q. Of text. If at all it exists. Let us return to Q. Now, we know that Q is complete. That is, there exists So what to do? So what we do is we bring in some hypothetical elements which we call the limit of such sequences. Some or objects as that's how we build it up. We have the set of rationals, and on the real line, so-called real line, we found that there are a lot of points which do not correspond to a rational number through the scaling that we adopt on that line. That means it is full of holes. And how to peg the holes? I mean, this is the elaborate construction process that we normally do. Of course, traditionally by introducing what are called cuts. So each cut corresponds to a new object which can be realized as the limit of a Cauchy sequence in Q. That is one method. The second method is, of course, the same thing. It's all the same thing. We construct a new space. A new space is essentially the set of all Cauchy sequences made up of rational numbers. Okay. And then in that we introduce a metric, not arbitrarily chosen, but chosen as an extension of the metric that you would have corresponding to the rationals. For instance, there are rational numbers which of Cauchy sequence of rational numbers which converge to a rational number. For example, if you take any rational number, then consider the sequence where all the elements of the sequence are the given rational number. Then you see that it's a Cauchy sequence, and that can be identified with a rational number. Okay. Now, how do we set up the collection of or the new space? So what we have done is the following. Consider Q tilde consisting of all Cauchy sequences rationals. That means the set of all the collection of where xn is and now we reflect back. Take a real number. What we have obtained through this process is the set of all reals. Now we see that if you take a real number, the real number can be obtained as the limit of a rational sequence. Okay? But such a rational sequence is not uniquely determined. So every real number some this is all from classical analysis. However, there are many Cauchy sequences elements in Q with its limit as the same that's a problem. So if you take Q tilde, you will see that several Cauchy sequences converge to the same real number. Okay. So you cannot just identify one such Cauchy sequence with it, but all these are equally competent to represent the particular real number. So how do we manage the situation? Here you see that the various rational sequences which represent the same real number are related to one another. Observe that any two rational sequences which the same real number are related to one another. But how? This is what we have to examine. So what we have is this. Suppose and then we observe that the distance between or we are taking rational sequences goes to 0 as infinity. It's quite easy to see because mod xm is less than or equal to mod And because of the convergence of xn to x and yn to x, see that goes to 0, which implies so two sequences which produce the same real number are not totally unrelated. They are related in some other. Whereas if you look at two sequences which produce which converge to different elements. For example, you have the set of a sequence of rational numbers which converge to root 2, and a sequence of rational numbers which converge to E. Okay, these two are not related. You don't have a relation like this in this form. Okay, so if mod xn minus yn does not tend to 0. In fact, it converges to what is called a root 2 minus modulus of root 2 minus 2. Okay. So you see that all Cauchy sequences of rationals which converge to the same element in R are related to one another through this relation. That is, xn is the sequence and yn is the sequence, then mod xn minus yn goes to 0 as n tends to infinity. Okay. So we shall now formulate them. But we do not have R, we do not know R exactly. So what we have obtained is this from Q. So we have Q, the set of rationals. Then you have Q tilde, the set of all Cauchy sequences of rationals. These two are there. Now what we do is, we want to identify each Cauchy sequence with a new object, because it is not possible to identify that with an object in Q, because some of them do not have this identification. Now, for example, you see that is a Cauchy sequence. Or what you call the constant sequence. This is the constant sequence. So the constant sequences in Q converge to elements in Q. And if there is any other sequence, for example, look at these sequences. The sequence 1 by n, this converges to 0, and so also 1 by 2 to the power n, this also converges to 0. So it need not be constant sequences. In fact, you have this sequence 0, that is every element is 0. This is also a Cauchy sequence which converges to 0. So all these things are related in the sense that, see, this condition is satisfied. Mod xn minus yn goes to 0. Okay. So what we do is we bundle all those sequences which are having a relation of this kind into one package. Okay. There are it's a bundle of Cauchy sequences which are related to one another in this type of relation. Okay. So we will just explore this idea bit further. I mean, I am not being rigorous at this stage. So we let they are Cauchy sequences of rational numbers. Infinity. Okay. So that defines a relation on Q tilde. So what is the relation? We say that xn is related to we shall say that is related to yn if and only if this is related to yn if and only if all we are slowly building up from our experience. So we have now with a relation defined, and we shall denote this by okay. What kind of relation is this? Now we observe that that's obvious. So it is a reflexive to xn related to yn if and only if or implies That is because mod xn minus yn is the same as mod yn. So this is true. So this is symmetric. Now the third property is we examine whether it is transitive. So yn implies this is easy to see. This is easy to see because we have similarly yn now you see that Zn, and if this side goes to as goes to 0. That's easy because this goes to 0, this goes to 0. Only that it's non-negative, therefore this is true. So the third relation is that hence and it is transitivity relation is transitive. So it is reflexive, symmetric and transitive. Therefore, what do we have? It's an equivalence relation. Therefore, Q tilde and therefore it partitions it. Equivalence classes. So what we have is this. This is what you call Q tilde. Now on which you have. So if you take an element here and an element here, they are not related. That's what we mean by partition. Okay? So it is partitioned into equivalent classes. Now what we prove is the following, that you get something extra than what we started with, Q. Okay? So this equivalence classes contain all elements of Q. How does it? So X, see, you have Q, X belongs to that, X is identified with the constant sequence X, Q2. So each X is identified with this constant sequence X in Q tilde. So you have a counterpart of each element of Q in this class. But we have much more. These counterparts. And this constitutes so that is the way in which R is constructed, and this is Cantor's construction. So what we prove is this: if X is any metric space, we can its completion. Through this procedure. So we have our experience of going from Q to R, and we resort to the same technique to work on any metric space to arrive at its completion. So I think that's a nice place to stop, and we now take up the problem in all its generality in our next lecture. Thank you very much.